Hello everybody. In this video we are going to be looking at the solution to the Physics 1 electromagnetic spectrum due right now, number 2. I think it's number 2. I'm doing so many of these I can't remember which one I'm on. Let's go with it being number 2. If I'm wrong, oh well. Let's see. First thing they want us to do is find the velocity of the observer for each of the following situations. Assume the light source is stationary in each situation. So in our first situation, an observer approaches a light source at a velocity that makes red light at a wavelength of 670 nanometers appear yellow, or have a wavelength of 585 nanometers. Let's take a look and see what we are given in this problem. It tells us that we have red light. So this is going to be the wavelength of the source. So the wavelength of the source is 670 nanometers. And it's going to appear yellow. So if it appears yellow, then that is my observed wavelength. So my wavelength of the observer is going to be 585 nanometers. The wavelength of the source is going to be 670 nanometers. I know that the light is going to be traveling at our universal speed limit of 3.00 times 10 to the 8th meters per second. That's our value for c, which is our speed of light. And we are trying to find the velocity of the observer. So we're solving for velocity. So I know I'm going to have to use the velocity formula here. But remember that velocity formula does have a positive negative sign. So let's take a look and see what we need for that. And because I know that the light source is stationary, and it says that the observer is approaching the light source, that the astronomer and the light source are moving toward each other. They're getting closer together. And because this is a wavelength formula, we have to make the velocity negative. So to make the velocity negative, I know that using my, my wavelength equation, the observed frequency minus the frequency of the source is going to equal the velocity divided by the speed of light times the wavelength of the source. When I rearrange this to solve for velocity, I'm going to have the velocity is going to equal the speed of light times the observed wavelength minus the source wavelength divided by the source wavelength. And I plug all of those numbers into my formula. And remember, my source wavelength is larger than my observed wavelength. So when I plug that into this portion, I'm going to end up with a negative number. And when I do all that math out, I'm going to have a speed of the observer of negative 3.8 times 10 to the 7th meters per second. One quick note on this problem. You may be saying, yo, Tiesler, wait a minute. You did not convert my wavelengths from nanometers to meters. And in this case, I don't need to, because if you think about your dimensional analysis never goes away. Don't tell anybody. No, actually tell everybody, because that's important. But because I have nanometers in my numerator of this fraction and nanometers in the denominator of that fraction, they're going to cancel each other out. I'm solving for meters per second. So this is really what I'm solving for in terms of units. Because they cancel out, I don't need to do the conversion. If you're unsure about when to convert and when not to convert, always convert, because you still get the right answer if you convert. Sometimes if you don't convert, in some situations you might end up with the wrong answer, but if you convert to our base units, you'll never end up with the wrong answer. So you don't need to in this case. You could still do it, and you're not wrong if you do, but if you don't want to do it in this particular case, it's not completely necessary. Part B states an observer approaches a light source at a velocity that makes a yellow light at a wavelength of 585 nanometers appear blue and have a wavelength of 470 nanometers. So the wavelength emitted by my source is going to be the yellow light, which is 585 nanometers. That's the wavelength of the source. And the observed wavelength, because it says it appears blue, the observed wavelength is going to be 470 nanometers. C, as always, is our speed of light to 3.00 times 10 to the 8th meters per second. And as with the previous part, we are looking to solve for velocity. And once again, the observer is approaching the light source, which means that the light source and the observer are moving toward each other. And once again, we are using the wavelength equation. So using the wavelength equation, if the relative motion is toward each other, then the velocity is going to be negative. So I start off with my wavelength formula, as I did beforehand, going to rearrange it and solve for velocity. I'm going to plug my known values into this equation, and once again, I don't have to convert my nanometers to meters. You can if you want to, and if you feel more comfortable doing that. In this particular case, it doesn't matter. Sometimes it will, but in this case, it doesn't matter. And when I do that math out, I am going to have a velocity of the astronomer or the observer of negative 5.9 times 10 to the 7th meters per second. Part C tells us an observer approaches a light source at a velocity that makes a red light at 670 nanometers appear blue at 470 nanometers. So our source wavelength is 670 nanometers. Our observed wavelength is 470 nanometers. C is always 3.00 times 10 to the 8th meters per second. And as before, we are looking for the velocity. And we're going to solve this one the same way we did the other two. I know this is getting a little repetitive, but this is the last one of these we have to do. Once again, because the observer is approaching the light source, the relative motion between the observer and the source is toward. And using our wavelength equation, if the relative motion is toward each other, we have to have a negative velocity. So we take our wavelength equation, and as we did before, we are going to solve that for velocity. We are going to plug in our known values for C and our observed and source wavelength. And when we do that, we are going to have a relative velocity between the source and the observer of negative 9.0 times 10 to the 7th meters per second.